background. So first off, I'll motivate the problem of why do we even want to care about diverse planning. So my take on it is that models are typically imperfect. So people, they go to your planning system, they have in their mind something they want, but they can't exactly model it all the time. So you can give back a set of solutions, and hopefully one of those solutions is something that they want. So this is what you would typically see when you use an information retrieval system like Google. It comes back with a bunch of relevant yet diverse results. And from that, you can kind of narrow down what you exactly want. So that's similar motivation here applied to planning. The other thing you can do with it is it can be useful for generating training data for learning HTNs or macro actions. So the goal of this work is looking at how do you diversify essential parts of plans. So imagine we have a plan, looks like this. We can diversify this plan in a couple of ways. We could make it add some nice interior or some doodads on the outside, or we could soup up the engine and add some machine guns. So depending on what your goal is, your diversity, your relevance is going to be different. So I can come up with scenarios where I might want one of the cars on the right, but I'm having a harder time with the ones on the left. So how do we know our plan set is diverse? Well, the typical measure that people have used, and I'll be using as well, is we have a set pi of plans. And we're looking at basically the average inter-plan distance. And so prior works have looked at 3 different types of distances. First is action set difference, and I'll illustrate that one. State set difference, and also causal link set difference. So action set distance looks like this. We want to compare the distance between pi and pi prime. We take the function A is just going to return the set of actions that appear in the plan. So the triangle there, I'm denoting the symmetric difference. And so it's the size of the symmetric difference over the size of the union is the proportion of unique actions appearing across these 2 plans. So you can define the state and causal link distance similarly. You just extract those features from the plans instead of just the actions. So the problem with this is it can favor plan garbage. So you can often have plans that have a lot of additional actions in them. So you do A, you undo A, you do B, you undo B. So looking at how do you actually measure required differences in plans, the first thought that came to mind was you want to compare the causal proofs, because this is the minimal essential aspect of the plan, and you want to compare those. But doing that is going to require doing something like edit distance, and it's going to be very expensive. So the next best idea is to use landmarks. Landmarks are something that appear in the causal proofs. They're essential to the plan as long as they're sound. But the problem is that they're incomplete. We don't get all of the features of the plan that might be different that are actually essential. But the nice thing about it is they're very cheap to use to compare plans. And the feature of them that we'll be exploiting is that they can often be disjunctive. So landmark distance is computed similarly to the action set difference, except what we do is we sum over for every one of the landmarks that appears in our disjunctive landmark set. We look at how many of those disjuncts are satisfied by one plan versus another plan. And then we take sort of the average of all of those disjuncts satisfied among all the disjunctive landmarks. So I want to give you an example of how we might fool the action set distance measure. So imagine we have 3 plans here, pi 1 through pi 3, and they are different routes through this little network here. I want to go from node 0 to node 2. So these are all feasible plans for this problem. If I want to draw your attention to pi 1 and pi 2 includes going from 0 to 1a, and then down to 1AR, and back to 1a, and then finally to 2. So this is a relevant reversible action that can be added to the plan. And what happens is it makes the plan look more different because I've added these extra actions. So if you look at the number of unique actions appearing in the symmetric difference among these pairs of plans, I get 2, 4, and 6. And when I remove those redundant actions, what I get is a less distant set of plans. So what does this tell you? If you want to increase action distance, add actions. The next thing you can do is take a domain like this where you have not irrelevant actions, but redundant actions. So actions that have some of the same effects that are ultimately necessary for achieving your goal, but the differences between those actions is fairly minimal. So in this example, what I've done is I've had pi 1 and pi 2 are basically the same path going from 0 to 1a to 2, but they're taking slightly different actions. So here they're using T1 versus T2. Imagine this is taking just a different truck. But it doesn't really matter which truck you take to get to your destination. And if you were to look at the lifted causal proofs for these two plans, you would see that they're identical. So here I have this T1 and T2. You can lift that out of the causal proof. So that basically it's just some truck. And those causal proofs become identical. Okay, so how would we do this with landmark distance? Well, let me point out the landmarks of this problem. We trivially have our goal state being one of the landmarks, which is denoted by phi 3. And then I have a disjunctive landmark here saying that I definitely have to go through 1A, 1B, 1C, or 1D. So there's a disjunctive landmark of size 4. And then I know I have to start in location 0. So when I compare these plans, the distance between them does not change by removing irrelevant actions, because I'm just looking at how many of the landmarks in common they have between them. Okay, so pi 1 and pi 2, they're going to both go through 1a, and that's the same landmark, so they only get to count that against once. So when I have this other network where I have redundant actions, you see that, again, I'm going through the same states. And they're satisfying the same landmarks. So it doesn't contribute anything to the distance between the plans if I were to, say, use a different truck. Okay, so how do we break this? Well, imagine we have a road network like this where we have, instead of 4 states that or 4 different disjuncts in our phi 2, we just have 2, which is 1a and 1b. And then we have these 2 subgoals, 1a prime and 1a double prime for 1a, and then 1b prime and 1b double prime for 1b. Now, those aren't landmarks. So here's an opportunity for me to add a essentially different route, but I can't see it because they're not landmarks. So this is one of the downfalls of this approach. And so what I want to stress is that it motivates new approaches for identifying disjunctive landmarks that perhaps use subgoals that do not appear in all plans, but they appear in a subset of the plans. Okay, so the algorithm I built around this is built on LAMA. It's called Diversify. Very simple algorithm. What you need to do is select k sets of landmark disjuncts, and then you need to force LAMA to satisfy that set. Okay, so making LAMA do that is not too difficult. The first thing you need to do is modify its landmark count heuristic. So the landmark count heuristic you need to basically modify the landmark graph to say, I've chosen this disjunct, and you're only allowed to count this landmark as being satisfied if you are satisfying the disjunct that I care about. The next thing you need to do is you need to make the landmark count a part of your goal test. So you have to make sure that you've actually satisfied all of your landmarks in order to say the plan is valid. In that way, you know that you've satisfied all the landmark disjuncts that you've chosen to satisfy. The final thing you need to do is you need to reopen closed search nodes. But because the landmark count heuristic is part of your goal test, it's often possible that you might have seen a node and then you are able to find it with a lower landmark count heuristic value and you want to reopen it. So by default, LAMA won't let you reopen the search nodes. And that's it. So another aspect of this algorithm is it's greedy before search and not during search. So what it does is it selects these landmark disjuncts ahead of time. And in comparison to the prior works, what they do is they find a set of solutions, and then while they're searching, they compare their partial solutions against the ones they've previously found. So this incurs a larger overhead in the search because you're constantly comparing your partial solution against the set of solutions you found. But here you can basically decide ahead of time what are the properties of these solutions in terms of the landmarks, and then I can solve them all in parallel if I wanted to. Okay, so in this instance here, what I could do is I could say, well, I want to solve 4 instances of this problem. The first one I solve for going through 1A, the second one I solve for going through 1B, and so on. So I can decide ahead of time what are the landmarks I want to satisfy. So what this looks like in the general case is if I have a bunch of disjunctive landmarks at the top here, So x1 through x3 is one disjunctive landmark, has 3 disjuncts, and so on for the others. What I want to do is I want to compute hitting sets on these disjunctive landmarks. So I would select x1, y1, z1 would be a possible candidate set to invoke DLAMA on. So how do you break this? Well, imagine we have a planning problem that looks like this, where we have 1A and 1B. Those are 2 disjuncts and a disjunctive landmark. All the way through 11A and 11B, those are also 2 disjuncts. Well, what if I were to select 1A, 2B through 11B? Well, there's no way to find a plan that will satisfy all those disjuncts. It's impossible. So in this case, there's 2 power 11 different disjunctive landmark sets, and there's only 2 that are actually going to be solution-bearing. So this is a hole in this approach that this problem will kill it. So I wanted to evaluate, how well this landmark distance compares to some of the prior works in terms of action set distance. And so the main question I wanted to ask is, what is the relationship between action set distance and landmark distance? And then furthermore, does this algorithm find high landmark distance sets of plans? So under the first question, I've listed 3 relationships. So it might be that if I find high action set distance plans, I could also have high landmark distance plans. The same set of plans would have a high landmark distance. Then I could have the opposite relation where if I have a set of plans that have high landmark distance, does that mean they're automatically going to have high action set distance? Or are they going to be roughly equivalent? So as a preview, this is what my experimental results showed, is that when you typically have high landmark distance, you're going to have high action set distance, but the opposite does not hold. Mainly because you can fool the planners into including lots of junk in the plans. Okay, so the experiments I compared against 2 other planners. The first is called FF greedy diversity. And what it does is it modifies the FF heuristic with a random element to it that also measures the diversity of the current solution with respect to the solutions already found. So it runs FF multiple times in order to generate a set. LPGG is a diverse version of LPG that is very similar. It adjusts its heuristic with the action set distance of its current solution against the previous ones found. So the tasks that are being solved are each of the planners is asked to find 4 plans per plan set. I also ran experiments with 16 and 64, and the results were pretty similar. And both of these algorithms up here are randomized, but DLAMA is deterministic. So I ran averages of 4 random seeds. And then LPGD also has a parameter that says how different did the plans need to be. So 0.01 means that the action set distance on average is 0.01 or 0.5 or 1.0. So I developed 3 artificial problems, the ones I showed you earlier, that I developed scalable versions of those. And then I developed or took the IPC problems that had disjunctive landmarks. So the first one was the irrelevant navigation. So this problem scales by repeating this structure you see on the graph on the right n times. So if this is a 2-step solution, you could have, for n, you have a 2n step solution. So what we see here is in the top right corner is the performance of DLAMA, and then I have the others shown here as well. So this graph is showing the plan set distance, the average plan set distance among all the plans. And so when DLAMA is set to 0.01, it still finds sets of plans that are doing well in terms of action distance, but then when you increase this distance measure, it finds more diverse set. But using DLAMA, we're able to find completely different sets of plans, and we designed this domain so this would happen. And basically, the reasons that they're completely different is it goes through different landmarks. So it's, in this case, having diversity in the landmarks that you satisfy implies diversity in the actions that you use, because the actions used to reach each of these landmarks is different. So what's the price of using action set distance? Well, In this case, you can increase action set distance with all of these planners. So what I'm showing here is the length of the plans found by DLAMA and the competitors here. And I've shown LAMA as a reference. So LAMA and DLAMA find the same length plans. And the others, they include these reversible actions, so they have longer plan lengths. So this illustrates that they're tempted to include these irrelevant actions. So in terms of total time, this also affects LPGD quite a bit because it's trying to do a local search. In order to find a diverse set, it has to do a much broader search in its search space. And the way that LPGD works is it looks very locally. So it has to go a very long distance in order to find a diverse set. In the redundant navigation, we see something similar. But in this case, it's easy to get high action distance because there's so many actions available to you, because you have repetitions of actions reaching these landmarks. But in order to really get a lot of landmark diversity, you have to use something like DLAMA. So this is showing the action distance along the x-axis and the landmark distance along the y. So you get perfect distance when you're using DLAMA. Finally, this domain where we thought we were going to kill DLAMA, it actually performs similar to the other approaches. And this is not saying that DLAMA is better. It's saying that the other approaches can't handle this problem very well either. And in terms of runtime, DLAMA tends to be a lot faster on this instance, even though it is not able to find completely diverse solutions. And it's more of a says more about the other planners than it does say about DLAMA, because it's showing that they have a very large search space in order to find diverse solutions. Okay, finally, these are results on the IPC instances. So what you see here is DLAMA is the only one that can find high landmark distance. And most of the solutions of the other techniques, they fall into having higher action distance, but not necessarily higher landmark distance. So what this suggests is that there are varying aspects of the problem that are not relevant to the landmarks. It's not to say that they're not diverse. It's just saying that perhaps DLAMA did not identify those aspects as landmarks, because it's ultimately limited by the landmarks that are identified by LAMA. And then you also see that the price that you pay for using these other approaches is that you would typically increase your average plan length because you're including these extra actions. And we also see that as a reference, LAMA, we're not finding sets of solutions that are terribly worse than LAMA. That's finding a single best solution. And this is about runtime. We're a little bit slower than LPGD, much slower than LAMA, because obviously we're solving a harder problem finding a set of solutions. And we're much faster than the FFGR div. So to summarize, action set distance does not imply when you have a high action set distance, it does not imply that you'll have a high landmark distance. So even though your plans look different, they might not be essentially different. The other thing about landmarks is they're going to be diversifying the essential aspects of your problem. And they're amenable to doing parallel diverse planning, where you can solve a set of completely different problems independently because you decide ahead of time what are the landmark disjuncts you want to satisfy. But it also, this work motivates new landmark extraction techniques that can help DLAMA improve diversity. So the more disjunctive landmarks you have, the more opportunity you have for diversification. And finally, the nice thing about this new distance measure is that you can integrate it with any of the existing plan diversity distance measures. So where it might lack in finding all the landmarks of the problem to diversify them, it can make up by integrating with, say, action set distance. So with that, I'll take your questions. Thank you.
Any questions? There are methods out there for diversifying search whose aim is not to find diverse plans, but to speed up search to prevent you from getting stuck in plateaus and bogged down. Rick Valenzano had a paper here, and there's other methods too. Have you looked at how diverse those solutions are? If you were to rerun, like Rick's system just randomizes a lot of stuff. If you run it twice, you'll probably find a different solution. I'm wondering how diverse those are and if we even really need these new methods.
Well, LPGD is a randomized method that's finding different plans. The thing is that it's starting from one of the existing plans and permuting it to become a new plan. And so it's looking at a different search space than some of these other planners, like an FF planner, base planner would be doing. And so what you get with this is you know that you're getting essential diversity, whereas with a randomized planner, you're not really sure what you're getting.
But we're not sure what we're getting, so shouldn't it be measured?
I'm sorry, I don't understand.
Maybe it's already achieving what you're trying to achieve. Maybe it's getting landmark diversity. Like, shouldn't it be a baseline in the study?
I'm not aware of that work, so I didn't include it, but definitely it should be compared against. Yeah.
Any other questions? Okay. So, do you think it's worthwhile at all to, so given that you're working with these landmarks, do you think it's worthwhile to include in which order these landmarks are being achieved to factor into the diversity calculation at all?
Sure,
And,
that's another way of adding diversity is the order in which you satisfy the landmarks.
Okay, so I guess, do you think that that would be an extension of your work, or do you think, is that being handled already? No, right?
No, it's not. And actually, the reason this work came about is I was doing some work on software testing using interaction testing to select inputs for programs. And they were essentially doing the same idea where you permute the inputs in order to make different inputs. And one of the things they've looked at recently is looking at alternative sequences of events in the systems and using those as different testing criteria. So that's certainly an avenue for new work.
Thanks.
Dan, could you put it on slide 31? I think it's the one I wanted. Yeah, you said that action distance doesn't imply landmark distance, if I got that direction right. But that, I think you left open that landmark distance implies action distance. But I couldn't make sense out of this graph.
Well, the point I wanted to point out here is that most of the solutions with the action distance optimizing approaches, they're going to fall in the lower right-hand corner.
Sure, but if I look at what DLAMA is finding, it's all over the place. You've got high landmark distance and low action distance, and you've got high action low landmark and high landmark low action. You've got both, right? So if one was driving the other, wouldn't you expect it to? You get one or the other, but not both of them. I mean, I've thought about this for as long as it took you to get from slide 31 to 34. So I may have missed something, but that's what I'm
right. So
confused about.
What's going on here is that we're using LAMA, and there's a lot of things going on in LAMA that are hard to control. So it's
yeah.
What's going on is we're not necessarily. We can also include reversible actions in LAMA because LAMA's reachability heuristic might do that. The landmark heuristic will kind of not encourage it to do that, but it can happen because of the fact that it's using other heuristics to guide the search. So that's the reason it's a little bit all over the place. What I took away from this is that optimizing action distance isn't going to get you landmark distance, whereas optimizing landmark distance, you at least have your landmark distance, and as a benefit, you might also get action distance.
That was a fairly weak claim, I think. I mean, what you said early on was landmark distance implies action distance, and then you said the reason it doesn't show up here is because LAMA's got lots of other stuff happening, which I.
Right, it's harder to draw claims about these IPC domains that don't have as regular a structure as the toy problems that I illustrated. On those, certainly it's the case that the implication should hold.
Should hold or does hold?
Does hold. Empirically, it holds. So here we see that on this particular problem, all of the action distance-based approaches, they typically are optimizing action distance, but they have to give up landmark distance in order to do that.
Okay, thanks.
Okay. I will ask one before we move on. So did you try to find the relation between the landmark distance and other distance that you mentioned at the beginning, like the causal link and also
state set?
So the causal link and state-based
Yeah.
distance,
Do they
those,
have any correlations like the action set?
I only choose action set because it's illustrative of the same problems you're going to run into with those other measures, that you can fool them in the same way that you fool the action set distance.
All right. You have one, two? Or? I have a couple more, but let's move on to the next talk. Let's thank the speaker again. And